Okay, so next unit is all about forces. This is chapter 4 in the book, although I am going to throw in some additional problems from some other books. But it should be a little shorter than the last unit. Okay, so far we studied the kinematics. Kind of describes how objects move, what's their velocity, acceleration, displacement, etc. But now dynamics is just why are they moving? What are the forces behind these motions? If there's an acceleration involved, there's a force creating that. So this was first explained by Sir Isaac Newton. You all know he has 3 laws of motion, which we'll go through. And we're discussing forces, like I said. So what is a force? It's very basic level. It is a push or a pull. It is still a vector, so directions are going to matter. We're still going to use some trig. There are 4 natural forces, 2 of which should be familiar to you. The other 2, probably not. And when I say natural forces, you sort of field forces. There's no contact necessary. And the number 1 that we're most familiar with is gravitational force. Compared to the rest, is actually fairly weak, but it does act over very long distances. Again, I'm being pulled to the Earth right now, even though I'm not on the surface of the Earth per se. So I don't have to be touching the Earth to feel that gravitational force. The electromagnetic force, imagine holding 2 magnets together. It is fairly strong force, but over a short distance, decreases quickly as distance increases. Same is true for gravitational force as well. But strong nuclear, weak nuclear, these forces are sort of within the atom itself. We won't talk about them too much other than to say sort of what holds the nucleus of an atom together. These can be really strong, but they act over, such a small distance inside that atom. All right, Newton's laws of motion are simple terms. The law of inertia, F equals ma, and action-reaction. All right, so first law of inertia. An object with no net force acting on it remains at constant velocity, and that can mean rest. Probably a little different version than what you learned in 9th grade. Physical science, you probably learn an object in motion stays in motion, or an object at rest stays at rest, unless there's an outside force acting on it. This is saying the same thing, and we can understand that as soon as we learn, of course, what net force means. But a net force is just the vector sum of all the forces acting on an object. Now, vector sum, that means direction matters. So if I am pulling to the left in a tug-of-war game, someone else is pulling to the right, and we're each pulling with the same magnitude, the net force is 0. So direction matters. We would add up those vectors like we did back in Unit 1. But anyway, if there's no net force, something's moving at constant velocity, which is another way of saying it's not accelerating. All right, so what's the net force on the following boxes? We actually, used this same slide in 9th grade. But like I just said, if you got left, right, same magnitude, please don't tell me that the net force is 10. The net force here is nothing. They cancel out. Directions matter. 3 to the left, 5 to the right, that's definitely a net of 2 newtons to the right. Here we've got 4 forces, and we can make a vector diagram where we keep adding these off of each other, find the resultant, tail the first, head the last. But you can clearly see left and right cancel, and I've got 1 newton extra up. And over here everything cancels out, so we have no net force there. So which box will have the greatest acceleration? That's getting into Newton's second law, F equals ma. Bigger the force, bigger the acceleration, assuming mass is the same. But the biggest acceleration would have to be top right, because it's got the biggest force. And then which boxes won't accelerate would be the ones with 0 net force. Now, just be careful. Just because these two won't accelerate doesn't mean they have to be still. That's a common misconception I see. That would be an easy, typical case where something is at rest. But imagine, let's say an elevator, we'll talk about an elevator a little later. There's a force that accelerates the entire elevator upwards, you included, because obviously you start at rest and then you get going, so there is a force that accelerates you upward. But for your entire trip up a tall building, you are not going faster, 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 all the way until you slam into the top floor. You know, you accelerate for a moment and then you maintain a constant velocity, you know, up until you slow down, stop, get off the elevator. That whole middle chunk, you're going at a constant velocity. That doesn't mean there's no forces acting on you, that just means the net is zero. Because clearly there's the weight of the entire elevator, and then there's sort of a tension force pulling you up. So please don't think that something with a net force of 0 on it has to be still, it just is not accelerating. Alright, although several forces are acting on this car, the vector sum of the forces is 0, thus the net force is 0 and the car moves at a constant velocity. This forward force, by the way, would be friction with the tires in the ground there. You know, if there was no friction, the car would just be spinning its wheels in place, like on mud or ice. And we are bringing up, I guess, some air resistance there. But certainly cars travel without accelerating all the time. You can set the cruise control, move at a constant velocity. Doesn't mean there's no forces acting on the car. They're just all 0 net force. All right, the term inertia has its own little definition. It means resistance to change in motion. Newton's first law is the law of inertia, but the word inertia itself means resistance to change in motion, and it is based simply on mass. So you've got a mouse and an elephant, you know, moving at you at the same speed. You know, which one's going to be harder to change what it's doing? Which one will be harder to stop? Obviously the elephant, okay, it's got a lot more mass, unless you're afraid of mice. Okay, the term equilibrium, that comes up in science all the time. You probably learned it in chemistry for balancing equations, or maybe the equilibrium of your inner ear. Basically it just means balance, but it's a state in which the net force is 0. So if there is no net force, then that object is considered to be in equilibrium. In equilibrium, objects, again, can move. They're just not going to accelerate, like the elevator example. It can move up at a steady pace. It's just not going faster and faster and faster if the forces are balanced. When there is a net force present, the objects will definitely accelerate. So objects that are either at rest or constant velocity are said to be in equilibrium. And these are sort of key words that we'll look for in some of the problems that we do. Does it say the box is at rest? Does it say it's at constant velocity? If it tells you one of these things, you know all the forces should balance out. All right, Newton's second law, F equals ma. Technically, we throw in a little sigma sign, meaning the sum of all the forces, in case there wasn't just one force acting on your object. But the net force is proportional to the mass of the object times its acceleration. Like I said earlier, the bigger the force, the bigger the acceleration. Assuming mass is the same, you can come up with different scenarios that relate to this, so long as you're discussing force, mass, and acceleration. You know, if you're driving and you've got a whole bunch of people loaded in your minivan, you know, if the mass has gone up and you still try to floor it, still try to provide that same force, you are not going to accelerate as fast as you would if you were driving by yourself. Likewise, stopping, you know, if you're applying a braking force and you've got a huge mass, you know, it is going to take you longer to come to a stop. So plan ahead. Don't learn that one the hard way. Units. Technically, we're still basing this off of the fundamental units. Mass is a fundamental measurement. That's in kilograms. Now acceleration is based off of length and time, meters and seconds, but together, kilogram meters per second squared is what we call a Newton, after, of course, Isaac Newton. All right, and third law, action-reaction. If two objects interact, the force exerted by object 1 on object 2 is equal and opposite the force exerted by object 2 on object 1. In 9th grade, I say all the time, you punch me in the face, my face is going to punch your hand right back. There's two objects that need to be involved, okay, my face, your hand. But there's always an equal and opposite force between them. We'll ask later in the year, which force is greater, the force of the Earth pulling on the moon or the force of the moon pulling on the Earth? Well, they're actually the same force, equal and opposite gravitational pulls. Because the forces coexist, either force can be called the action or reaction, does not matter which is which. Consider driving a nail into wood with a hammer. The force that the nail exerts on the hammer is equal and opposite to the force the hammer exerts on the nail. But there is a net force acting on the nail which drives the nail into the wood. Okay, other types of specific forces that we'll talk about, weight. We've already talked about gravity, but the force of gravity is called an object's weight. Gravity is what gives an object its weight. So if we're talking about forces, I'd like you to use the word weight instead of gravity. Normal force, friction, tension. So let's go through those. Weight, like I said, is a gravitational force exerted on an object by Earth. It's a vector quantity. It's always going to point down towards the center of Earth. And weight changes with the location of an object in the universe, but mass does not. So if you go to the moon, you have the same mass, but you're definitely going to have a different weight because there's a different gravitational pull on the moon. Here's another equation for us. We already have F equals ma. The weight equation is essentially F equals ma. It's just that weight is a force, specific force. There's your m. And a, gravity, is a specific acceleration. All right, dealing with weight on an incline. Let's see. Okay. Incline problems are kind of common force problems that we'll see. And when we're dealing with weight on an incline, I said weight is always straight down. And when we draw a little vector indicating the different forces acting on an object, it's called a free body diagram. But sometimes it's not helpful to talk about weight when you have an incline because now we've got some angles involved. And we can see that our inclines, aligned like this, they're sort of perpendicular to the incline. And it's actually a lot easier for us to find components called weight parallel, that means parallel, and weight perpendicular. And these are sort of like the x and y components of a vector. The reason it's nice to deal with weight perpendicular, weight parallel is because, maybe we've got friction involved. That's going to be parallel to the incline. Maybe there's a rope pulling this box down. That's going to be parallel to the incline. So it'd be nice to have everything in the same line. And I can deal with weight parallel easily instead of the weight. Likewise, weight perpendicular is, again, perpendicular to the surface. We're about to learn about normal force. Normal force would be straight up from the surface. So by finding weight components like this, it does kind of keep all our forces in line. Also conveniently, you will very likely be given the angle of an incline. That angle fits in nicely right up here. If you drew it this way, if you drew weight perpendicular first, then weight parallel to make weight the resultant of those two. You can kind of prove that, I guess. Like, if this were a 30-degree angle, and this is 90, this would be 60, you know, for this triangle. So at the top, you know, this is a 90-degree, one big 90-degree angle. That component's 60, so this would have to be 30. So if you're given the angle of the incline, it sort of just fits in the top of your weight triangle. All right, like I mentioned, the normal force is the force from a surface. So if I'm standing on flat ground, the normal force on me right now is straight up. Normal force can only come perpendicular from that surface. So if your surface is slanted, normal force will be 2. It's just got to be perpendicular to it. Different books abbreviate it different ways. Force, normal. I'm just going to stick with capital N for normal force. One less letter makes it a little easier. Okay, so friction is a force I'm sure you're familiar with. Friction is a force that opposes motion between two surfaces. We know that from physical science. We're going to break it down, though, in physics for between static friction and kinetic friction. And the word static just kind of means still anyway. But static friction is what exists before something is moving. It's the friction that resists the moving of something in the first place. Kinetic friction is what is present when something is already moving. And we have a little friction equation. Say friction is fun, kind of looks like F-U-N, fun. That's the force of friction. That's the normal force. And we'll talk about what that little Greek letter is. That is Greek letter mu. And it's called the coefficient of friction. And it depends on what type of surface you have. So obviously certain materials are going to provide more friction than others. You know, we got rubber on dry concrete. That's a static friction coefficient of 1. Kinetic friction coefficient of 0.8. And static is always going to be greater than kinetic. It's always harder to get something going than to keep it going. Notice your synovial joints in humans. You know, you don't want a lot of friction when your joints are moving back and forth and your bones are moving. So those are really, really low values, but of course, they're not 0. Somebody with arthritis probably has a higher frictional value there, causing some of that pain. But note that kinetic is always lower, and they're usually decimals. Not always, but usually decimal values. And there's no unit, sort of a ratio of the force of friction and the normal force. So there actually is no unit to the coefficient of friction. All right, we'll just quickly mention air resistance and then ignore it. Air resistance is a form of friction. Whenever an object moves through a fluid, and remember air is considered a fluid as well, gases and liquids are fluid, there is some resistance to that object's motion. For a falling object, when the upward force of air resistance balances the downward force of weight, gravitational pull, the net force on the object is 0. So skydivers, for instance, you know, according to our physics class, they would accelerate all the way till they hit the ground. But in reality, that's not true. Skydivers reach terminal velocity based on their weight, based on their shape, how aerodynamic they've made themselves, whether they have a parachute or not, whether they pulled the parachute yet or not. But they will reach maximum velocity, let's say in the ballpark of 200 miles an hour for a typical skydiver who has not pulled their parachute yet. But this would be called terminal velocity. And you know, it's where the object is not accelerating, like I said. And it wouldn't be accelerating because the upward force equals the downward force. Air resistance up equals weight down. So constant velocity. All right, another force, tension, If you have a force in a rope or a string, something's being pulled by a rope, we just usually call that T for tension. And I mentioned we were drawing some free body diagrams already. But drawing free body diagrams to show forces is a really helpful tool when solving force-based problems. So basically a free body diagram, free body means you just kind of draw the object. You don't have to draw the scenery, anything around it. And then you draw as vectors all the forces acting on that object. So if you took honors physical science, you've done some of this already. But quick sketch of free body diagrams. I'm going to throw one more in here. A book sitting on a table. All right, there's my book. I don't need to draw the table. You can. I'm just going to draw the object. All the forces acting on it based off of that information are simply the weight of the book and the normal force up. Now, presumably this book is still. It is not crashing through the table. It's not magically flying off the table. So if it's at rest, these forces need to be balanced. And my picture should sort of indicate that. The length of this weight vector arrow should be the same length as the normal force arrow. Nothing going left and right. Done. All right, a baseball flying through the air. Again, there's always weight. And weight is always straight down towards the center of the earth. But is there anything else I can put on there? Technically, yes, there'd be air resistance. But I'm going to leave off air resistance. We're going to pretty much always ignore that. Normal force, well, it's not touching a surface. It's not on the ground yet. Tension, there's no string. Now, there was a force from the bat a while back that got it going, but at this moment, at this instant in time, that's it. That's all you can draw for your free body diagram. We said last unit, there's no natural horizontal acceleration. There's no sideways gravity, no sideways weight. So that's it. I know that it's moving through the air, so you really want to throw something else on there, like the velocity vector. Well, that's not a force, that's a velocity. It is moving to the right because it has inertia, because it was already moving to the right. Why was it moving to the right originally? Okay, well, yeah, because it was hit by a bat. There was a force originally to the right to move it to the right. But it is no longer accelerating to the right, so there's no force left or right. All right, a baseball at the instant it's hit by the bat would look similar. I've got weight down, and now I can throw on the force from the bat. It's a contact force. I'm just going to call it FB. And certain contact forces you can describe however you feel appropriate, like that. All right, one more. I don't think it's on here. You've got a couple practice free body diagram problems you can do, but I just want to make sure I do show one full incline problem. So let's just say we have a box moving at constant velocity up an incline. And it's pulled by a rope. Okay, I do like to draw the inclines when we have an incline problem. Then you can draw your box. And now the force is acting on this box. All right, for one, it says it's being pulled by a rope, and it's being pulled up the incline. So I'm going to call that a tension force. But we have three other forces acting on this box. Weight is one that I said we can always draw on there. So we have weight, but it is really not helpful to deal with just weight in an incline problem. We really want those components. So start back at the top, right at the box, and I like to draw weight perpendicular first. Again, perpendicular to the incline, and then from there, weight parallel. And make sure you've tried to line this up so weight parallel, is parallel to that incline. Don't make it flat with the ground. You want it parallel to the incline. And this would be your little 90-degree triangle right there. In addition to that, this is on a surface, so we have the normal force. Normal force, again, can only push straight out from the surface, so this is at an angle as well, not straight up. And friction. And if this says it's moving at a constant velocity, then I know forces are balanced. I know that that tension that's going up and to the right needs to equal everything else going down to the left. I know that must be true. Forces are balanced left and right, and also sort of up and down, so I know the normal must equal weight perpendicular. And once I've drawn in weight perpendicular and weight parallel, I'm never going to use weight again. I'm using those two vectors to represent that one. So this is a case where a really good picture can help you solve a problem. Okay, quick friction question. We have these two formulas for friction. Really look exactly the same, right? We got F equals mu N. I made a lowercase f this time. Sorry, different books, different versions. Same thing though. Force of friction equals coefficient of friction times normal force. Friction is fun. There's a subtle difference between these two though. This is just saying the kinetic frictional force will be equal to the kinetic friction coefficient times the normal force. Sure. But this doesn't just say the static frictional force equals coefficient times normal. It just says the maximum value. So if you are solving for something related to static friction, you got to be a little wary if the object's not moving. Because if the object's not moving, well, maybe you've reached that maximum possible value of static friction, but maybe not. So here's a little scenario. It says, what's the static friction, I should say static frictional force, acting on a 1,000 kilogram crate at rest, where the coefficient of static friction is 0.5, that's being pulled by an infant with a force of 2 newtons to the right. Okay, so static frictional force. I'd like to just kind of plug in here, maybe see if I can figure out what static frictional force is. Mu is 0.5. And then N. All right, well, what is N? Quick free body diagram. I got weight down, normal force up. It does say this object is at rest, so I know all these things sort of equal out. Ups equals down, left equals right. So in this case, normal force equals the weight. And then the weight equation that we'll always use is mass times gravity. So we've got mass of 1,000. Times 9.81. Note that I didn't make it negative 9.81. I'm just finding the magnitude of this value. I know normal force is up. I know weight is down. I'm just trying to find the magnitude for a second. All right, so multiply that out. half of 1,500, 500 times 9.81 is 490.5 newtons. And this is what I get for the maximum value of static friction. That is not the answer to this question. What is a static friction, or frictional force? The static frictional force is not 490.5 newtons, because look at what would happen if it were. The frictional force, 490.5 newtons to the left, and this infant is pulling with 2 newtons to the right. Those clearly aren't equal. This object is at rest. So in this case, the baby could pull all the way up to 490.5 newtons before this thing starts to move. But that doesn't mean the frictional force is always 490.5 newtons. The frictional force will increase until the baby reaches that maximum possible value. So if the baby is pulling 2 newtons to the right, the frictional force is 2 newtons to the left. That's the only way to balance out the baby. 2 newtons to the right, 2 newtons to the left. Friction could be equal to 490.5. So just be wary when you're using that equation. This just gets you the maximum value of static friction. It does not mean that is the amount of static friction in your problem. It could always be less. So try to pay attention to the context of the problem. All right, why are anti-lock brakes a good thing? And same answer here. Why is it more difficult to start something moving or keep it, or is it more difficult to start something moving or keep it moving? Both of these boil down to static friction is greater than kinetic friction. Anti-lock brakes, anti-lock, they prevent your tires from locking. And if your tires lock, then really your whole car is sliding along the ground trying to come to a stop. And if it's sliding along the ground trying to come to a stop, it's kinetic friction that's trying to make you come to a stop. That is less than static friction. If you have anti-lock brakes, it just kind of intermittently stops your tire, but your tire is still rotating. So no one point on your tire is ever sliding on the ground. One point on the tire is always in contact with one point on the ground. Therefore, there's no sliding, and it's static friction that would bring you to a stop. This one I think you know. It is definitely more difficult to get something moving than to keep it moving. Same idea, because static friction is greater than kinetic friction. On a microscopic level, you can partially think of the roughness of the surface. You know, once something starts moving, it smooths out a little bit. Partial explanation there. Okay, just going to mention elevators again. When referring to a person standing in an elevator, there are only 2 forces acting on the person. There's, of course, the weight down and the normal force on that person up. Now, yes, there's tension in the cable pulling the entire elevator up, but we just want to talk about just the person for a second. So at certain points around an elevator, you might feel like you weigh more or less. And this is not because your weight has changed at all. You always have the same weight because you have the same gravitational pull. But because the normal force has either increased or decreased. And in this case, since you sort of feel like you weigh more or feel like you weigh less, the normal force is referred to as your apparent weight. We mentioned that in roller coasters too. What's your apparent weight? Because at certain points in the loop of a roller coaster, you might feel heavier or lighter. So I think you intuitively know where you would feel heavier or lighter, but we can kind of prove this with a little free body diagram real quick. So draw free body diagrams, given these scenarios. So in every single case, I'm going to draw weight down, same distance, like same magnitude. that does not change. Gravity didn't change, 9.81. The guy's mass didn't change, so weight does not change. But the normal force is going to. And you can sort of see why. First, at rest on the ground, okay, there's that key word at rest, means forces are balanced. So the normal force would have to be the exact same magnitude as the weight. Now, if we are speeding up, okay, then we need a greater force up. So the normal force would be really big there. And that is where you would feel heavier. And if you were actually standing on a scale in an elevator and you looked down, it would read heavier than your weight, sort of being pushed into you. All right, constant speed. Constant speed, same keyword as rest. Forces are balanced. So the normal force should still be the same size as the weight. And now if we're slowing down, moving up, but slowing down, the net force should be down. So the normal force should be little. Weight should sort of win out there. And that is where you'll feel not really weightless, but less heavy than you normally do. Your apparent weight is going to be lower than what you actually weigh on a scale at rest. All right, so those are our elevator problems. Elevator free body diagrams. All right, now we're just going to run through some common example problems, something you might see in the homework. I do recommend a picture for even the most basic problem. Draw a free body diagram for all of these. This one says a student pushes on a 1 kilogram book on a horizontal table with a force of 5 newtons. The book is just about to move, but still at rest. Find the coefficient of friction between the book and the table. All right, the book is just about to move. That's another kind of key phrase we look out for in physics. Just about to move means that the maximum value of static friction has been reached. Any, infinitesimal newton past that is going to make this book accelerate. But just about to move means that we've reached that maximum value of static friction. So, book on a table, I'm just going to draw the book. Forces acting on it, obviously weight has to be there. Normal force is there from the table pushing back. We can say we have push force. And friction would be preventing it from moving forward. So friction has to be the other way. FF for force of friction technically be like static. But there you go. Okay, find the coefficient of friction between the book and the table. Coefficient of friction. Well, that automatically makes me think of the friction formula. And I can't get that until I know the force of friction and the normal force. But I've got a good free body diagram. I know that this book is still at rest, so I know forces are balanced. I know ups equal downs, lefts equal rights. So I know the normal equals the weight, and I know friction equals the push force. Weight, don't forget that weight is a force, weight's in newtons. A lot of times people confuse mass with weight. 1 kilogram is a mass. So I do need to do mass times gravity to actually get that weight, to actually get that normal force. So 1 times 9.81. Of course, that's still 9.81, so now it's in newtons. So now I can kind of plug on in over here. Force of friction must be equal to that push force, which was 5 newtons. Just divide, and we're done. 0.51. And that's also a decent clue that we're correct, is that it is a decimal. Usually the coefficient of friction is going to be a decimal. All right, so there's a basic friction problem. Again, my free body diagram helped me know that some forces were equal, so I could plug into that friction equation. Okay, let's sketch this one out separately. A student attaches a rope to a 20-kilogram box of books. Why you would drag your books like that, I don't know. He pulls with a force of 90 newtons at an angle of 30 degrees with the horizontal. The coefficient of kinetic friction between the box and sidewalk is 0.1. Find the acceleration of the box. Okay. So looking for accelerations is definitely a case where forces are not balanced. And we've got kinetic friction given. All right, so let me just sketch this box one more time as a free body diagram. We'll try to label all this. There's the box. I have weight. I have normal. Since it did say a rope, I'm going to call that tension off at an angle. Friction is not helping. And since I have that angle, and everything looks like it sort of lines up, tension's the odd one out, I'm going to make components there of tension. Tx and Ty. All right, let's see what values I can throw in here. We got 20 kilogram box, 90 newtons, angle of 30. And then mu was 0.5. Okay, so that's all my labeled given information. And again, the question was, what is the acceleration of the box? So I'm in my forces unit, acceleration, I'm thinking F equals ma. But before I dive too far into that, you've got something at an angle. Again, most common first step when you have something at an angle is to find those components. I'm not going to use 90 degrees in this problem. I'm going to use Tx and Ty, whatever they are. So just do a little trig. We got 90 cosine of 30 and 90 sine of 30. If you know your 30, 60, 90 triangle, the side opposite the 30 degrees is like your 1, 2, square root of 3. You're welcome to do the trig. So that should be 45. Again, 1, 2, square root of 3. So this should be 45 times square root of 3. I'll do that out. Or just 90 cosine of 30. Okay, so I have my components. I'm also just going to take a second to find weight. Almost always going to want to do that too. Weight, mass times gravity. So you get 196.2 newtons. So we've got all our forces labeled so far that we know. All right, now back to my question of finding the acceleration of this box. And it's definitely going to be accelerating to the right. So what, without using numbers, what do I know that's true about these forces? First of all, if it is accelerating to the right, I know that there is a net force. And the net force is essentially Tx. That's my main force moving this box to the right, but friction is not helping. Friction's going back the other way, so I've got to subtract out friction. I also know, as far as ups and downs, that the box is not accelerating up or down. So ups should still equal down. So I know that n plus ty, being the ups, equal weight, which is the down. And I'm already taking into account my direction here, up is equal down, so I'm not going to make weight negative. And now, okay, so that's helpful, but how does, A come into play at all here? Well, net force F equals ma, this equals ma. So getting a little messy. I'm going to set this back up with numbers now. So m is 20 times A equals Tx, 77.9, minus friction. Now, I don't know what friction is, but I do know friction is also mu times n. Well, I'm given mu, that's 0.5. But I still don't know n yet. But pretty easy to find since I have this little equation right here at the bottom. Let's see if I can get myself just a little distance. I want to find n. And here's a good case where n does not equal weight. Often weight's down, normal's up, end of story. But I have another force that is partially pulling up. That tension is supporting some of the weight. So I've got to take into account that. So Ty is 45, and weight we said was 196.2. So the normal force, again, is not 196.2. But 196.2 minus 45 is 151.2. And now I can plug that in up here. And solve for A. So I get 0.115 meters per second squared to the right. Again, is a vector. Put a direction on there. So a little longer problem. This is a good one where the forces were not balanced. That's probably about half the time the case. But if you have an accelerated situation, remember that you have a net force. Doesn't mean that net force equals one particular thing, like Tx. But you've got to consider everything in that direction where it's accelerating. If it's accelerated to the right, I need to consider everything right and everything left. Left is not helping, so sort of subtract out the left. So F equals ma. In that case, the net force was Tx minus Ff. Also good to note that normal force was not equal to weight here. Isn't always. We had that rope that's supporting some of the weight. So they did not need to be equal. Okay, another typical forces problem is an incline problem, something on an incline. In this case, we have a 1 kilogram book is at rest on an incline of 30 degrees. It is just about to slide free, but it is not moving. What is the coefficient of static friction between the book and the incline? All right, so again, we sort of see that phrase, it's just about to move. So that means we've reached that maximum value of static friction. Let's start with a little sketch. Okay, there's my box on my incline, or my book, I guess. I've got weight, of course, coming down. Throw my little angle there. Also have normal force perpendicular. And if it's not moving and it's on an incline, the only reason why it wouldn't be moving is because of friction. So based off this picture, of course, it would want to go down and to the left, so friction must be up and to the right, preventing it from moving. Go ahead and draw your components of weight. Remember, if you draw weight perpendicular first, that same angle of the incline can go up top here, 30 degrees. And then weight parallel. Try to draw it again so the parallel component is parallel to the incline. And that's about it. There's no tension, there's no rope, nothing else is acting on this box. So the question says, what is the coefficient of static friction? I know that's only going to come from this formula. Friction is fun. FF equals mu times N. I've just got to come up with FF and N. So looking back to my picture, let's try to get some numbers on here. The only thing I really know is the mass and the angle. But knowing the mass, I can get the weight. Weight is mass times gravity. 1 times 9.81. So of course weight down is 9.81 newtons. However, I'm not going to use that number in this problem other than to find the components. So let's see, we got 30, 60, 90 again. Weight parallel will be opposite my 30. That's always the, the 1, 2, square root of 3. So half of that, 4.905 newtons. Or again, you could just say 9.81 sine of 30. And then weight perpendicular would be cosine of 30 times 9.81. Or 4.905 times square root of 3. And I get 8.5. A little rounding. Okay. So I pretty much put up the numbers I can get just based off of that given information. Now I need to look at my picture. I know that I want the force of friction. I know that I want the normal force. None of those are labeled right now, but I know how they relate to weight perpendicular, weight parallel. So again, imagine this whole x and y axis is sort of tilted. So as far as left and right, I know that weight parallel down has to equal friction up and to the right. And in this direction, normal sort of coming out of the incline's got to equal weight perpendicular going into it. So I know my components, and now they're directly related to FF and N, and I can just plug on in. Force of friction is weight parallel is 4.95. Again, newtons. Normal force is weight perpendicular. It's 8.5. So just divide. Looks like we'll definitely get a decimal. We get 0.58. And that will be the coefficient of static friction since it was not moving. Okay, good incline problem. Again, the angle of the incline is given, and you draw your weight triangle like this, it will go in the top. All right, one more problem. All right, tension problem, something hanging. It says a hanging sign has a mass of 150 kilograms. If two wires support the sign and there's an angle of 100 degrees between them, what is the tension in each rope? All right, make a sketch. Okay, so there's our hanging sign. We have two ropes, 100 degrees between them, so a symmetrical setup. Weight's pulling it down. There's no normal force, there's no surface it's sitting on, there's no friction, because there's no surface to provide the friction. So this is it. I do have an angle, don't like angles, so I do like to find components. And the nice thing is that this is symmetrical, so the Tx on either side is equal. And it would have to be anyway, because of course it's not moving left or right, it's just hanging there. Ty's will be equal too. So we've got 100 degrees. So if you have 100 degrees between them, and you know, sort of like half a circle is 180, these two chunks would have to be 40 and 40. So 40, 100, 40, that adds up to 180. So I'm just going to analyze one triangle, and I know it's symmetrical, so that'll be the same. So, okay, and that's my goal. I'm trying to find tension in each rope. So, things I know, obviously the angle, but I know it's kind of obvious, I guess. Tx equals Tx. And I could have called this tension 1, tension 2, and said, Tx1 equals Tx2, either way. Or I've got Ty plus Ty, both going up, equals weight down. Or 2 Ty's equal the weight going down. And I do know the weight going down, because that's mass times gravity. Mass is 150. Gravity is 9.81. So I get 1,471.5 newtons is the weight, which I will plug in here. Divide by 2, and now I have Ty. Not the answer to the question, but now we're very, very close. What is the tension in each rope? Okay, now it's just a trig problem. I know Ty, I know the angle. I can find the hypotenuse. The hypotenuse is the tension. So I want that, I know the angle. So I know the opposite side, and I want the hypotenuse. That's going to be sine of 40 equals opposite over hypotenuse. And then just solve for t. Of course, make sure you're multiplying t to the other side first and dividing by sine of 40. to get 1,144.62. Voila.